Hello students, welcome back to my channel. We are so glad to see you here. Stay tuned for more exciting content and feel free to engage with us in the comments or share your thoughts. I hope your JEE preparation is going fantastic and you are also revising the content periodically. Consistent revision is the key to solidifying your understanding and boosting your confidence. Keep up the hard work, stay focused, and remember, every bit of effort brings you closer to your goal. Today we are going to start with permutation and combination, and this is our 8th session on this chapter. And today's content is all about multinomial theorem and application of multinomial theorem. Along with that, derangement problems. Don't forget to subscribe, like, and share the content with others. Your support helps us grow and bring you more amazing content like this. Stay tuned and let's keep the learning going. Let's dive right into today's topic. Thanks once again for joining us. So let's start our today's class with multinomial theorem. First, let us read the theorem and then I will make you understand what does this multinomial theorem demands. The theorem states that if there are A objects of one kind, B objects of another kind and C objects of another kind and so on, then the number of ways of choosing means we are talking about selection. Selecting R objects out of these objects are same as finding the coefficient of x to the power r in the expansion of these three polynomials that I have written. Okay, now the question is how these polynomials are coming. See, there are A objects of one kind. So what are the options that you have of choosing these A objects from this kind? Either you will select no object, which I have written it by x to the power 0, or we can choose one object from this, that is why I have written this thing as x to the power 1, or we can choose two objects, x squared, or we can choose three objects, x cubed, and so on. And maximum we can choose A objects. That is why it is 8x to the power A. Same thing with the other polynomials also. Now, whenever we are writing x to the power some exponent, this exponent actually signifies how many objects of that category you are choosing, and the coefficient of that x to the power how many objects we have chosen gives us, this coefficient gives us in how many ways you can select that amount of object of that kind. That's it. Just remember this. The exponent signifies how many objects of that category are chosen, and the coefficient of that x will give us in how many ways that amount of object can be selected. Is it clear? Let us try to understand this theorem by means of an example. Let us say there are three objects of one kind and there are four objects of another kind. Now I want to select, not arranging, only selecting. I want to select 4 objects out of this. Now, suppose if we don't use multinomial theorem, then how we will solve this? We will find out the different cases. Let us say this group be A and this group be B. Now, let me consider what are the possible cases where we can select only 4 objects. This is group A and this is group B. I can select 3 objects from group A, 1 object from group B, or I can select 2 objects from group A, 2 objects from group B, or it can be 1 object from group A, 3 objects from group B, and no object from group A, and 4 objects from the second category or group B. Now, how many different ways you can choose 3 objects? These are all alike objects. So in how many different ways you can choose 3 objects from group A and 1 object from group B? It is only one way. Again, I am telling you, the objects of each group, they are alike. All the objects of group A, they are alike. All the objects of group B, they are alike. So there is only one way of choosing 3 objects from group A and 1 object from group B. Again, in the similar way, 2 objects from group A and 2 objects from group B, this can be selected in one way. Similarly, 1 object from group A and 3 objects from group B, again one way. And the 4th one is again one way. So there are total 4 ways of choosing or selecting 4 objects from these 2 categories of objects given to us. Now, let me try to do the same sum by using multinomial theorem. So you have to select 4 objects. So what I will do, I will simply find out what is the coefficient of x to the power 4 in the expansion of. Let us consider the first group. We are having 3 objects. So what are the possible ways? What are the possible ways you can select the objects? I can select the object x to the power 0. X to the power 0 means I am selecting no object from this group. Or I can select 1 object, so it is x to the power 1. I can select 2 objects, so x to the power 2. Or I can select 3 objects, which is x to the power 3. Okay, this is for your category A. And what about category B? I can choose no object from category B, or 1 object, or 2 objects, or 3 objects, or 4 objects, right? So from this polynomial, I have to find out the coefficient of x to the power 4, and we will see that it exactly matches with the number of ways that we have calculated when we have considered cases. Let us check it. How to get x to the power 4? When x to the power 0 is multiplied with x to the power 4, we are getting the coefficient of x to the power 4 as 1. When x to the power 1 is multiplied with x cube, we are getting the coefficient of x to the power 4 again, which is 1. When x square is multiplied with x square, we are getting x to the power 4 and the coefficient is 1. And when we are taking x cube and x to the power 1, so again we are getting x to the power 4 and the coefficient is 1. So again, the total number of ways in this way if we do, we are getting there are 4 ways, which exactly matches with the answer that we have done previously. Is this clear to all of you? So you see, here you should not be in the judgmental mode. Say whether this method is lengthy or that method is shorter. Don't go for that. Here we are learning a method. We are learning a method. Always remember that this kind of problems, when you find that the objects are alike of different kinds which are given to us, in that case we can either consider cases or we can directly apply the multinomial theorem. in this example, the example that we have taken, what we have selected, there are two categories given to us. One category is containing, let us say the category is A, it is containing 3 elements, and category B is having 4 elements. Now I have to select 4 elements out of this total available objects. So by using multinomial theorem, what I have done, I have simply found what is the coefficient of x to the power 4. How many number of objects you have to draw, you have to find out the coefficient of that. Here we have to select 4 objects. So we have to find out what is the coefficient of x to the power 4 in the expansion of, which expansion? Category A has 3 objects. Now what are the available possibilities you have for choosing objects from category 1, category A? Either you will choose no object, or 1 object, or 2 objects, or 3 objects. Same thing with category B. Either I will choose no object, or 1 object, or 2 objects, or 3 objects, or 4 objects. So you simply multiply that and find out the coefficient of x to the power 4 from that expansion to get in how many different ways you can only select 4 objects out of that. That's it. And again, I have solved this problem by using your case consideration also. Right? Have you understood this multinomial theorem? Okay, let me take another example. Let us say we are having the word IITJEE. Now if I ask you in how many ways we can select 4 alphabets from these available alphabets given in the word IITJEE. So we have to find out 4 alphabets. We have to only select 4 alphabets. That's it. So actually we have to find out here x to the power 4, the coefficient of x to the power 4. Always remember, whenever we are writing x to the power n, this n means how many objects you are choosing. I have already mentioned this. Again, I am telling you how many objects you are selecting, and the coefficient always signifies in how many ways you can select that n number of objects. Always remember that. So we are finding out the coefficient of x to the power 4. That is, we are finding out in how many different ways 4 objects can be selected from which expansion. So for that we have to see, here we are having we are having 2 i's and 2 e's, right? We are having T and J as different alphabets. So we have to find out the coefficient of x to the power 4 in the expansion of, look it carefully, we are having 2 i's. So either I can choose no I, or I will choose 1 I, or I will choose 2 i's. That's it. For E, the same thing, x to the power 0, x to the power 1 plus x square. For T, either I can select T, or I will not select T. Same thing for J, either I will not select J, or I will select 1J. So it is basically finding out the coefficient of x to the power 4 in the expansion of 1 plus x square whole square into 1 plus x whole square. That's it. So how to find out this? In this case, what I will do, I will simply write this is 1 plus x square. This is whole square into 1 plus x whole square. So if I break this one by using a plus b whole square, we are having 1 plus x whole square plus 2x square 1 plus x to the power 4 into 1 plus x whole square. So if I multiply, we are getting plus 2x square 1 plus x whole cube plus x to the power 4, 1 plus x whole square. So from this expansion, I want to find out the coefficient of x to the power 4. From here we are getting the coefficient of x to the power 4 as 4c4. From this one, from this expansion, I need what is the coefficient of x square only. Why? Because that when multiplied with x square gives us x to the power 4. And the coefficient will be 2 times. The coefficient of x square from this expansion is 3c2. And from this, since we are having x to the power 4 outside, so I need only the constant term from this expansion. So that is 1. So the coefficient of x to the power 4 from this expansion is 1. Therefore, the total number of ways of selecting 4 alphabets from this word IITJEE is 4C4, which is 1. 2 times 3C2 is basically 3 plus 1. So that gives us 8 ways. That's it. Now, this question you can again solve it by considering the cases. Again, I'm telling you, at this moment, don't focus on that which method is shorter. We are learning a method. So try to focus on that. Okay. So this is how we use multinomial theorem to find out the total number of ways of selecting objects from the given available objects in which there are alike terms or alike objects involved. Is it clear to everyone? Okay, let me take another example. This sum, see, it has said that find the number of selection of 4 letters from the word assassination. Now in assassination, what we are having 3 A's, 4 A's, 2 I's, 2 N's, and 1 T and 1 0. So we have to select 4 letters from this word. That is, in multinomial theorem version, we will say that actually we are trying to find out the coefficient of x to the power 4 in this expansion. How I have written this expansion, try to understand this. Here there are 3 A's. So here, what are the possibilities of choosing A? How many different ways you have of choosing these 3 A's? Either I will select no A, that is by x to the power 0, or I can select 1A, x to the power 1, or I can select 2 A's, x square, or I can select 3 A's, so x cube. Same thing with S, same thing with I, same thing with N, and same thing with T and O. I hope it is clear now. So now, this is for S selection, I selection, N selection, T selection, and 0 selection, O selections. Clear? Now, what I'm doing is I'm simply applying the GP formula. Every time whenever you find this kind of series, you always go for GP series and you find out the sum. So for the respective terms, I found the GP series, the summation of those series, right? Okay. So now what I'm trying to do here is, I can write this thing in this way. In the denominator, we are having 1 minus x 6 times. So it goes in the numerator. It becomes 1 minus x whole to the power minus 6. Now what I'm trying to do is, I want to find out the coefficient of x to the power 4. You should understand this. We have to find out the coefficient of x to the power 4. And that exactly what we will, it will give us the number of selection of 4 letters from this word, assassination, right? So now, let me just multiply these 2 terms to get 1 minus x to the power 4. You can ask me, sir, why you have not written the other terms? You see, if I multiply, what you are actually having, 1 minus x to the power 4 minus x to the power 5 plus x to the power 9. But see, while multiplying this, I have not written this one and this one. Why? Because these are all having the exponents more than 4. And in our problem, I don't need any exponent which is more than 4. Isn't it so? because I have to find out the coefficient of x to the power 4. What I will do with x to the power 5 or x to the power 9. So that is why I have not calculated or I have not multiplied those terms in the final result. Okay, so the next thing is there. And now what I'm doing is, for 1 minus x cube whole square, I have breaked it by using a minus b whole square. Again, this is a square minus 2ab plus b square. B square will give us x to the power 6. That is why I have not written it in my expansion. Because x to the power 6, this is more than x to the power 4, which I don't want. Okay, so in this case, now I will multiply this 2 to get this one. Please check it. While I multiply this first two factors, we are actually having 1 minus x to the power 4 minus 2x cube, then plus 2x to the power 7. You can observe I have rejected x to the power 7 coefficient because I don't need that. And for the second term, 1 minus x square whole square, I breaked it in a minus b whole square. We got this. Here all the terms of this expansion I have taken, because all the terms are having the exponent 4 or less than 4. So now if I multiply this 2, you are getting this. So we are having this thing ultimately. Is it clear? Please check it. The multiplication I have already done. So we are having this expansion. So now we have to find out the coefficient of x to the power 4 from this simplified version of the given polynomial. So from here what we will get? See, all we know from the binomial chapter, how to expand 1 minus x whole to the power minus 6. I told you that you must write this thing as 6c1 first, x, then it will be 7c2x square, and this thing goes on, right? Actually, the difference between these two, 7 and 2, is c5. 6 and 1, it's again 5. So if I ask you what is the coefficient of x to the power 10, you will say, sir, it will be c10. C10 will be there, but the difference is since 5, so this thing will be 15. Okay, that way we find out the coefficient of x to the power any exponent in this kind of expansion. This we have already discussed in binomial theorem classes. So now there is one. I need x to the power 4. So obviously from this expansion, I need x to the power 4 because that when multiplied with 1 gives us the coefficient of x to the power 4. And that is nothing but your c4. I need x to the power 4. So it will be c4. But since the difference is 5, so it will be 9. So the first case you will be getting 9c4, right? Now we are having square. So square, so I need x square from this expansion. What will be the coefficient? Here it will be 2. But since the gap is 5, so it will be 7. So that's exactly what I have written, 7c2 over here. And 2 is multiplied, so 2 is multiplied here, right? Then we are having x cube. So I need only x from this expansion. And that can be done in c1 because x to the power 1, it will be c1. Gap is 5, so it will be 6c1. So that's exactly what I have written, 6c1 over here. And now after calculating, we are getting 72. And that's your answer. Have you observed this? Have you understood the application of multinomial theorem? I can tell you this is very, very important theorem as far as your JEE problems are concerned. Because the moment you go for some critical problems when a lot of cases are there to be considered, in that case multinomial theorem acts as a blessing. So that is why you have to understand this multinomial theorem very clearly. So if you have not understood this, what I will suggest you, after this live class, you stop the video and then you rewind it and please see this portion again. Then only the thing will become very clear to you. Right? Okay. Now let us come for the same thing. You see, the only difference between the previous one and this theorem is that there we have considered the selection. Only selection. But here not only selection, but also arranging those R objects are considered. Very important. Here we are not only selecting R objects, at the same time we are arranging these R objects. In how many different ways we can do that? The same way. It is the coefficient of x to the power r in the expansion of this thing. Now, you can say that this part is little bit, more complicated than the previous version. No, it is not at all complicated. If you see this one, you will find it is so very logical. You see, the selection, when we are considering about the selection in the previous theorem, when we are considering only the selection, this factorial part didn't occur. Isn't it so? This factorial part didn't occur. But whenever this arrangement is considered, this factorial thing came into the picture. Why it is so? Very simple logic. Suppose we have chosen 4 objects. Let us say 2 of one kind and 2 of other kind. So now you have to arrange between them. So you are having 4 objects that can be arranged in factorial 4 different ways. But 2 objects are alike of one kind and 2 objects are alike of another kind. So that has to be divided by factorial 2. That's exactly what this theorem says. In this case, suppose if we want to find out x to the power 4 from, let us say, from this one and this one. Suppose we want to find out x to the power 4. So how to find it out? We have written this one as factorial 4. Look at carefully. I want to find out x to the power 4. So factorial 4 into, when this 1 is multiplied with, here there is another term, x to the power 4 divided by factorial 4. So when this 1 is multiplied with factorial 4, x to the power 4, that gives us the coefficient of x to the power 4. So here the coefficient will be 1 over factorial 4. Next, when this one is multiplied with this, then we are getting the coefficient of x to the power 4. So the coefficient will be 1 over factorial 1 into factorial 3. Similarly, when this is multiplied with this, we are getting the coefficient as factorial 2 into factorial 2, because these are all the coefficients of x to the power 4. And again, when this is multiplied with this, the coefficient will be 1 by factorial 3 into factorial 1. It is again the coefficient of x to the power 4. And one more we will get from here. Here there is the next term is x to the power 4 by factorial 4. So this when multiplied with 1, the coefficient is 1 by factorial 4. Now can you see the logic? The total number of ways we got by the coefficient. But whenever we are multiplying this is actually giving us the total number of arrangements. Because when you are selecting this, what do you mean by this? When you are selecting this, what is that? It is actually, you are taking 3 objects from this group, let us say A, and 1 object from group B. So now you are having 4 objects. These 4 objects can arrange among themselves in factorial 4 divided by 3 objects are identical. So divided by factorial 3, 1 object divided by factorial 1. So that exactly what we have multiplied here. 4 factorial 4 is outside. So when you multiply, it will give us like this. Factorial 4 by factorial 3 into factorial 1. You can consider this also. This is what? You are choosing 2 objects of one kind which belongs to your group A, and 2 objects from group B, which is again alike objects of that kind. So now you are having 4 objects. Now these 4 objects can be arranged among themselves by factorial 4 divided by factorial 2 into factorial 2. And that's exactly what written over here. Are you getting the point or not? The total number of ways of selecting is 1. The total number of ways of selecting this object is 1, because you see this is again multiplied with 1. Because whenever you are selecting, let us say this one and this one, the coefficient is actually 1. Because what will be the coefficient of x to the power 4 in the previous case? In the previous, when we are considering the selection, there we have considered the coefficient will be 1. Here also the coefficient is 1. But this factorial thing is actually playing the role for arranging those objects. That's exactly what has done here. So this theorem is pretty logical and we have to remember in this way. Is it clear? Let me take one example. So this question we have already done in my previous class. Find the number of words that can be formed by taking 4 alphabets from the word mathematics. This is a very, very popular sum, and the answer I always used to suggest my students that for this one, you must remember this result. It is 2454. It's a very, very common problem. Okay. So now the question is how many different words that can be formed by taking 4 alphabets. Again, all the case consideration I have already done in my previous classes. Those who have not seen those classes, link has been given in the description box. You can check it. But here we will apply multinomial theorem to solve this. Now we have to form words. We have to form words. It means they are talking about arrangement of the alphabets that are chosen. Okay, so for mathematics, we are having 2 M's, 2 A's, 2 T's, and H, E, I, C, S, they are all distinct. Now we have to actually find out the coefficient of x to the power 4 in the expansion of factorial 4 into this thing. Please check it. Why I have done in this one? First you understand this. Why I have done this? For the first one, for the first factor, why this power is cube? Because this actually signifies for 2 M's. 2 M's, 2 M's is what? Either I can choose no M, or I can choose 1 M, or I can choose 2 M's. Right? Same thing with A and same thing with T. That is why I have written this thing as whole cube. And for the 5 distinct alphabets, either I can choose that alphabet or I will not. So it will be x to the power 0 plus x to the power 1 by factorial 1. That's exactly what I have written 5 times. That is why the exponent is 5. I hope it is clear to all. Now we have to find out the coefficient of x to the power 4. Okay, let me just erase this. So now you see how I've done. I have simply made this thing. I am now breaking this one. I have taken 1 plus x squared by 2 whole cube. So now I am going to expand this by using the formula a plus b whole cube. So we are actually getting this. Is it clear? Now have you observed one thing? I have not considered the cube portion of the last one, because cube of this will give us what? X to the power 6 divided by 8. Now x to the power 6, I need only x to the power 4. So I don't need x to the power 6. That is why I have not included it. Okay? And now let me just multiply this. Now we have to find out the coefficient of x to the power 4. From this one, the coefficient will be HC4. From this one, already x square is there. So this will be your HC4. And this one, x square is already there. So I need only x square. So it will be 7C2. Here x to the power 4 is already there. So I need only 1 here. So that's exactly what I have written over here. Okay. So now if we simplify this, we are going to have this one. And we are getting the result as 2454. I hope this problem is clear to all. Again, this we have already considered. I have already done this by considering the cases. You can check it. Here we have done the same problem by using multinomial theorem. So I hope now multinomial theorem is clear to all of you. 2 things we have done. Whenever there is a question of selection, that is only you are selecting the objects, there this factorial part will not come. And when there is a question of arrangement, then this factorial part will come. These 2 theorems you have to learn and you have to remember this by heart. Okay. So now let us see where we can use this multinomial theorem in permutation combination. This is one place where we have used. Now we will go for some other parts of permutation combination where you can use this multinomial theorem. Now this is one another area where we can use multinomial theorem to find out the number of solutions. See, to find out the number of solutions, we have already done this part in our previous class, where we have used Beggar's method to solve, where the question was how many number of non-negative integral solutions of any equation which is given to us. Now we will try to solve the same problem by using multinomial theorem. But before starting this, can we justify ourselves that yes, in this kind of problems, we can use multinomial theorem? The answer is yes. Why? Let us check. The question is, find the number of non-negative integral solutions for this equation. Now my question is, can we use multinomial theorem here? Answer is yes. Why? Because here, actually what you are doing, you are simply distributing these 8 identical objects among 3 in such a way that this first, let us just consider this as my person, that the first beggar or the person, whichever way you say, can receive no objects, or it can receive 1 object, or it can receive 2 objects and so on, and maximum he can receive 8 objects. Same thing with the second person or the beggar. Same thing with the third person. The third person or the second person can receive again in the same way. Either they will receive no coins, or they will receive 1 coins or 2 coins or 3 coins or till 8 coins. So in this case, we can easily use multinomial theorem. Why? Because what we actually do, for the first person, if we consider, what we will say, that this person can receive no coins, this person or this beggar can receive 1 coin, or this beggar can receive 2 coins, and this thing goes on. Maximum he can receive 8 coins. Same thing for the second person. He will receive either 0 or 1 or 2. Maximum he can receive 8 coins. Same thing with the third person's 8. Am I correct or not? Now we have to find out the coefficient of x to the power 8 in this expansion. That's exactly what multinomial theorem states. Now, what I taught you? I taught you that whenever there is x to the power something, whenever it is x to the power something, this something represents what? How many number of objects, that particular person is receiving. And the coefficient, whatever coefficient is there, this coefficient represents what? How many ways the person can receive these n objects. Is it clear? So our main task is to find out the coefficient of x to the power 8 from this expansion. And that's exactly what it will say, the total number of, finding out the total number of non-negative integral solutions. Is it clear? Why it's non-negative? Because you see, x, y, z in all these cases can be greater than or equals to 0. And I have already considered that x can receive no objects. That is why I have considered x to the power 0. Same thing with y, same thing with z. So this answer will actually give us the total number of non-integral solutions for this equation. Am I correct? So let us try to find out what will be the coefficient of x to the power 8 in this expansion. We are actually finding out the coefficient of x to the power 8 in the expansion of 1 plus x square x to the power 8 whole cube. So that gives us 1 minus x to the power 9, 1 minus x whole cube. So that gives us 1 minus x to the power 9 whole cube into 1 minus x whole to the power minus 3. We have to find out the coefficient of x to the power 8. From this expression, we can cancel x to the power 9 because it exceeds x to the power 8. So we don't need to consider it. So from here, we are only having 1. So all the coefficient of x to the power 8 will come from this expansion. And that will be C8 over here. And the difference is, if I expand 1 minus x whole cube, whole to the power minus 3, it will be 1 plus 3c1x plus 4c2x squared. So everywhere the difference is 2. So here it will be, the difference will be 2 again. So here it will be 10. So total number of ways of getting non-negative integral solution for this equation is 10c8, which is same as your 10c2. Am I correct? Now, let me just cross-verify this answer with our Beger's method. In Beger's method, we are having x plus y plus z is 8, where all x, y, z are greater than equals to 0. So the total number of non-negative integral solutions will be 8 plus 3 minus 1, c3 minus 1. Those who have not seen the Beger's method, my previous class, I will suggest all of you first to see that video and then come to this video so that you will have a second option of doing this kind of problem, because this kind of problems are very, very important. So it is coming to 10c2 and exactly the same answer what we got. So I hope this question is clear to us. And we have understood one thing, that whenever this kind of integral solutions of any equation is given to us, we can solve it by multinomial theorem. Okay, let me take another problem. See this question. X plus y plus z is 8, but there is now restrictions. Your x is greater than equals to 0. Okay. Y is greater than 0 means y is greater than equals to 1. Z is greater than 1, it means Z is greater than equals to 2. So now we have to find out the total number of integral solutions for this equation. X plus y plus z is 8. Now let me try to do it by Beger method. This is the last time I am doing it, because after this sum, whatever problem we will do, we will simply do it by multinomial theorem. We will not go for Beger's method. Just for your convenience, I am doing this thing by Beger's method first, then I will apply multinomial theorem. So in this case, what will happen? What I told you, the shortcut method was, here it is 1 and here it is 2. So if you add 1 plus 2, it gives us 3. So simply write this 8 as 5 only, because 8 minus 3 gives us 5. Okay, so your x plus y plus z is 5. Now I can apply that formula. It's n plus r minus 1 c r minus 1. So that gives us 7c2, and that will be our answer. Now we will cross-verify this answer with our multinomial theorem. So is it clear to all? Because this is actually the method, what we call method of substitution, that I taught you in my previous class. At the same time, I taught you that if this kind of problems are given, so we can use the shortcut method of finding out the number of solutions. That's exactly what I have opted here. Now let us come for the second method, which is our multinomial theorem. So here what we will do, we have to find out the coefficient of x to the power 8 in the expansion of. Let us first consider x. So x can get 0, 1, 2, maximum it will receive 8. Therefore, for x, we will write the polynomial as x to the power 0, because x can receive 0 objects. X to the power 1, x square, maximum x to the power 8. Now for y, it is greater than equals to 1, means the minimum amount that y can receive is 1. Therefore, we should start the polynomial with x to the power 1, then x squared, then x cubed, and this thing goes on till x to the power 8. And for z is greater than equals to 2. It means what? Minimum objects that Z can receive is 2. So it will be x square. It can receive 2 objects or 3 objects or 4 objects, and maximum Z can receive 8 objects. Therefore, the total number of integral solutions for this equation, the equation which is given to us with the given condition, will be the coefficient of x to the power 8 in this expansion. So let me just try to solve this. This is actually a GP series, so I will write this thing as 1 minus x to the power 9 divided by 1 minus x. Now, let me take one x common from here. So we are left with 1 plus x square plus x to the power 7. And from here, let me take x square common. So we are left with plus x to the power 6. Am I correct? So it gives us what? Actually, we are having x cube 1 minus x to the power 9 over 1 minus x. 1 minus x to the power 8 over 1 minus x. 1 minus x to the power 7 divided by 1 minus x. Now we have to actually find out x to the power, the coefficient of x to the power 8. We already got x cube. So now what I need is basically finding out the coefficient of x to the power 5 in the expansion of Is it clear? So now, from this one, there is x to the power 9. I don't need it. So 1 is there. Again, from here, x to the power 8 is there. I don't need it. So only 1 is there. From here, x to the power 7, I don't need. So only 1 is here. So x to the power, the coefficient of x to the power 5 will come from 1 minus x whole to the power minus 3. And the coefficient of x to the power 5 in this case will be C5. Difference is 2, so it will be 7. Therefore, the answer is 7C2. 7C5 is same as 7C2. NCR is same as NCN minus R. Therefore, we have cross-checked this answer and this answer. They are exactly the same answer. So we have seen that whether you use Bayes' method or multinomial theorem, we are going to have the same answer. But yes, multinomial theorem is one other way of solving this kind of problems. Is it clear now? Okay, let's move for some other problems. So this question, find the number of non-zero integral solutions of the equation x plus y plus z. This equation is given and we have to find out non-zero integral solutions. That is, your x, y, z and w will be all greater than equals to 1 because it is non-zero integral solutions. Okay, non-zero integral solutions. So we have to actually find out the coefficient. Here we will straight away use multinomial theorem. So here we have to find out the coefficient of x to the power 20 in the expansion of, for x you will write x to the power 1 because the minimum value x, y, z and w will receive is 1. So we have to start the exponent of x with 1 for x, then x squared, then x cubed, maximum it can take the value x to the power 20. Same thing with y, same thing with z, so it will be q, right? Now, is it clear to everyone why I have given this q? Because this same expression will come for x, y and z. That is why I have not written these 3 terms again and again. I have simply raised it power to 3. Now the question comes about your w. Please check this one. Here what we are having? We are having the coefficient of w as 4. That is, look it very carefully. You have to understand this. Suppose if w takes the value 1, then this 4w will take the value 4. If w takes the value 2, then 4w will take the value 8. If W takes the value 3, 4W will take the value what? 12, and this thing goes on. Yes or no? So you have to understand this. This person, let me just denote this person by, let us say, P. So the person P can either receive 4 objects or 8 objects or 12 objects, and this thing goes on. So for P, we must start with x to the power 4. Why x to the power 4? Because this person, the minimum amount of the objects that this person can receive is 4. Then it can receive 8, then it can receive 12, then it can receive 16, then it can receive, or it can receive 20, because maximum 20 objects can come. So for W, be very careful. I have started the thing with x to the power 4. Is it clear? Because W, when W is 1, this 4W, that is P, is taking the value 4, then 8, then 12, and so on. That is why I have started the thing with x to the power 4. Okay? And then it moves on accordingly. And why I have stopped here? Because maximum objects that are available to us is 20. That is why I have stopped, because W can receive the maximum object as 20. It cannot exceed 20. That is why I have stopped here. Is it clear? So we have to find out the coefficient of x to the power 20 in this expansion. So what I'm trying to do here is, first let me take x common from this polynomial. We are getting x's cube will come out. So we are left with 1 plus x square plus x to the power 19 whole cube. And for this, if I take x to the power 4 outside, we are left with 1 plus x to the power 4 plus x to the power 12, x to the power 16. Okay? So from here we are getting x to the power 7. So we have to find out the coefficient of x to the power 20, but we already have x to the power 7. So actually we need to find out the coefficient of x to the power 13 in the expansion of this one. Am I correct or not? Please confirm me. Please write down in the chat section whether I am correct or not. Am I correct or not? Have you understood this? Okay. Now let's see. This is a GP series. So let me just use my GP formula. It will be 1 minus x to the power. How many number of elements are there? There are 20 elements or 20 terms. So it will be 1 minus x to the power 20 divided by 1 minus x whole cube into this whole thing. So this is coming like what? We have to find out the coefficient of x to the power 13 in 1 minus x to the power 20 whole cube into 1 minus x whole to the power minus 1 into 1 plus x to the power 4 plus x to the power 8 plus x to the power 12 plus x to the power 16. Now, from this, since there is x to the power 20, so no need to expand this. Even if you expand, the only thing that I will consider is 1. Because other terms, the other exponents will be more than 13 in this expansion, right? So I am only taking 1. So we are left with 1 plus x to the power 4, x to the power 8, x to the power 16 into, sorry, this is not 1, this is minus 3. So 1 minus x whole to the power minus 3. We need to find out what? We need to find out the coefficient of x to the power 13. Now look it carefully. For this expansion, the difference will be 2. Now, here it is 1. I need to find out x to the power 13. So the coefficient will be C13 and difference is 2, so it will be 15. We are having x4 here. So we need x to the power 9 from this expansion. So it will be C9. Difference is 2. So it will be 11. Plus, here it is x to the power 8. So we need x to the power 5 from here. Difference is 2, so it will be 7c5. For x to the power 12, I need only x. So it will be c1. Difference is 2, so it will be 3. And I don't need x to the power 16, right? Because it will exceed x to the power 13. So our final answer will be this, which actually gives us 15c2 plus 11c2 plus 7c2 plus 3. So this is coming like 15 into 14 divided by, that is 15 into 7 plus 11 into 5, 7 into 3 plus 3. So this gives us 105 plus 55, 21 plus 3, right? So we are actually having 160, 183, 181, 160 plus 21, 181, 3, 184. And that should be our answer. Thus the answer is 184. I hope it is clear to all of you, right? Let's move for the next problem. See this question. This is the same type of question but with a different flavor. Find the number of positive unequal integral solutions. Positive unequal integral solutions. You see, so far whatever sums we have done, here any object can go to any place, that is for x, y and z. Now it may so happen that your x and y are getting some objects which are equal in number. It may so happen, but no. In this problem, I want how many such solutions, positive solutions are there which are all unequal. That is, whatever amount x will receive, whatever amount y will receive, whatever amount z and w will receive, they are all different. They are all different. Okay, how to use this? Please check this one. Let us assume that without disturbing any part of this question, let us first assume that your x is less than y is less than z and less than w. This case is happening. That is, whatever amount x is received, it is less than the amount of y, less than the amount of z and less than the amount of w. Now, somebody can ask me, sir, why you have done in this way? It may so happen that your y is getting more numbers than your z, or your x is having more numbers than your w. Then why you have assumed this? Okay. I have taken one case, that x is less than y, less than z and less than w. Now, these four terms, x, y, z and w, they can interchange among themselves. In how many different ways? In factorial 4 different ways. So what I will do, first of all, I will find out all the possibilities for this case. When x is less than y, less than z and less than w. And then whatever solutions we are getting, we will simply multiply it with factorial 4 to get the total number of solutions where all these x, y, z and w are receiving unequal unequal numbers. Is it clear? That is, we are always getting, in this case, we are always getting unequal solutions for x, y, z and w. Is it clear? Okay. So, they are all positive. So, your x is greater than equals to 1. Y is, z is also greater than equals to 1 and z is also greater than, w is also greater than equals to 1. Okay, so, and the equation we have been given is x plus y plus z plus w is 14. So how to handle this? Let us say y is nothing but x plus k1. Your y is greater than x. I am introducing a dummy variable, let us say k1. such that if you add this k1 with x, we are going to have y. Is it clear? Similarly, z can be written as y plus k2 and w can be written as z plus k3. Now, in place of y, we can write x plus k1. So it is coming like x plus k1 plus k2. And this thing is coming like z can be replaced by x plus k1 plus k2 plus k3. In all these cases, your k1 will be greater than equals to 1. K2 will be greater than equals to 1. As well as your k3 is greater than equals to 1. Therefore, our equation, now this equation is transformed into x plus, in place of y I am writing x plus k1. In place of z I am writing x plus k1 plus k2. And for w we are writing right, which is equals to 14. So from here we are having 4x plus 3k1 plus 2k2 plus k3, which is equals to 14. And in all these cases, your x is greater than equals to 1, k1, k2, k3, all are greater than equals to 1. So how many such solutions are possible for this equation? So we have to find out the coefficient of x to the power 14 in the expansion of, first you please see this 4x. So what I will write? I will start with x to the power 4 plus x to the power 8 plus x to the power 12 and so on. But I will stop here because the maximum amount I can receive is 14. So when x becomes 4, 4x becomes 16. So 16 objects is not available. Only 14 objects are available. So we have to stop here. Is it clear? Now for k1, it will be what? X cube, x to the power 6, x to the power 9, x to the power 12. That's it. For k2, we are having x square, x to the power 4, x to the power 6, x to the power 8, x to the power 10, x to the power 12, and x to the power 14. That's it. This is for k2. And for k3, it will start from x, x square, x cube, and this thing goes on till x to the power 14. Am I correct? So we have to find out the coefficient of x to the power 14 from this expansion. So what I will try to do here is, first I will take x to the power 4 common from the first expression. From the second expression, I will take x cube common. From the third expression, I will take x square common. And from the fourth expression, I will take x common. So actually we are having x to the power 4 plus into x cube into x square into x, that gives us 10, right? So actually this is, we are finding out x to the power 14, coefficient of x to the power 14 in x to the power 10 into 1 plus x to the power 4 plus x to the power 8 into 1 plus x cube plus x to the power 6 plus x to the power 9. From here we are having 1 plus x square, x to the power 4, this thing goes on, x to the power, last term will be x to the power 12. And from here we are having 1 plus x square plus x to the power 13, right? So we have already received x to the power 10. We need to find out the coefficient of x to the power 14. That is, we actually need x to the power 4, the coefficient of x to the power 4 from the expansion of this. Am I correct or not? Please confirm me. Please write down in the chat box whether I am clear or not to all of you. Okay, so I need to find out the coefficient of x to the power 4 only. So from this expression, I will only consider, let me write it here. Okay, x to the power 4, we want to find out from this. From the first expression, we will simply write 1 plus x to the power 4 because I don't need x to the power 8. From the second one, I need 1 plus x cube only because I don't need x to the power 6 and x to the power 9. From the third expression, we need only 1 plus x square plus x to the power 4. That's it. And from the last expression, we need 1 plus x square plus x cube plus x to the power 4. That's it. Okay. So now, if I multiply this two, look it very carefully. If I multiply this two, let me write it here. So we need the coefficient of x to the power 4. If we multiply this, we are getting 1 plus x cube plus x to the power 4. That's it. Because I don't want to write the other expression, other term, which is x to the power 7. I don't need that. From the second one, we are having this. And from the third one, we are actually having 1 minus x to the power 5 divided. This is the GP series. So I have added that. 5 terms are there. So 1 minus x to the power 5 by 1 minus x. So now you need to find out the coefficient of x to the power 4 in this expansion. Now if I multiply this, we are going to have 1 plus x squared plus x to the power 4. Then when x cube is multiplied, it is only we are having x cube. I don't need the other terms. When x to the power 4 is multiplied, I need only x to the power 4. I don't need other terms. That's it. 1 minus x to the power 5 into 1 minus x whole to the power minus 1. Okay. So we need the coefficient of x to the power 4 in the expansion of 1 plus x squared plus x cube plus 2x to the power 4. 1 minus x to the power 5. From here, I need only 1 because x to the power 5 I don't need. 1 minus x whole to the power minus 1. So now, we need x to the power 4. So what will be the coefficient of x to the power 4? When 1 is multiplied with x to the power 4 from this expansion, we will get the coefficient of x to the power 4, which is 1. When x square is multiplied with x square of this from this term, we are going to get the coefficient as 1, which actually gives us the coefficient of x to the power 4. When x cube is multiplied, we have to multiply it with x from this last term. So that again, the coefficient is 1. And x to the power 4 is multiplied with the constant term to get the coefficient as 2. So the total answer will be 5. So this is our answer? No. Why? Because this is the total number of ways where your x is less than y, less than z and less than w. As I told you in the beginning of this question that this is one arrangement of the variables that are given. So now 4 variables can arrange among themselves in factorial 4 different ways. Therefore, total number of integral solutions that we will get, total number of integral solutions that we are going to have is 5 into factorial 4. That is 120, and that is your answer. Is this clear to all of you? So I'm trying to illustrate all kinds of possibilities from this multinomial theorem by using this multinomial theorem to solve the equation. Okay, all the varieties I'm trying to show you through these illustrations, right? Let us take another problem. In this question, they have said how many ways 15 identical blankets be distributed among 6 beggars such that everyone gets at least 1 blanket. 2 particular beggars get equal blankets and another 3 particular beggars get equal blankets. So there are 6 beggars Let us say the beggars be B1, B2, B3, B4, B5 and B6. Now, we have to distribute this 15 identical blankets among the 6 beggars such that everyone gets at least one blanket. Now, there are 2 particular beggars, let us say B1 and B2. There are 2 particular beggars which are going to get equal number of blankets, and there are 3 particular beggars, other 3 particular beggars, which are also getting equal blankets. Now, in how many different ways these blankets can be distributed among these 6 beggars? This is the question. Is it clear to all? Now, let us say that beggar B1 and B2, they get X blankets, and B4, B5, B6, they get Y blankets each, and B3 gets, let us say, Z blankets. So, according to the question, we are actually having 2X plus 3Y plus Z, which is equals to 15, in which your X, Y, Z all are greater than or equals to 1, because they are going to receive at least one blanket. So, how to solve this? Now, if I apply multinomial theorem, what we are going to have? We have to find out the coefficient of x to the power 15 in the expansion of x square. This is for your x square, x to the power 4, x to the power 6, x to the power 8, x to the power 10, x to the power 12, x to the power 14. That's it. I have to stop here because the total blankets available are 15. So I cannot go beyond this. Now, for y, the number of blankets received by y is either x cube or x to the power 6, x to the power 9, x to the power 12, x to the power 15. That's it. And for z, it will be x plus x square plus x cube, and this thing goes on till x to the power 15, because the maximum number of blankets that B3 can receive is 15 blankets, right? So now, we have to find out x to the power 15. Now, one thing let me just tell you, because this thing can come in your mind, that whenever we are considering x, y and z, we will consider the maximum number of blankets they can receive. I will simply forget what are the total number of blankets received by the other beggars. That I will not consider. Okay, because that will automatically get cancelled when we are going to find out the coefficient of x to the power 15. So we are least bothered about that. Okay, so we have to find out the coefficient of x to the power 15 from this expansion. So let me just take out x square from here, x cube from here, and x from here. So we already got x to the power 6. So we actually need x to the power 9. The coefficient of x to the power 9 in the expansion of 1 plus x square plus x to the power 4, x to the power 6, x to the power 8, x to the power 10, and x to the power 12, right? From the second one, we are actually having 1, x cube, x to the power 6, x to the power 9, x to the power 12. And from the third one, we are getting 1 plus x cube, so on, x to the power 14, right? Now, we can easily see that we don't need x to the power 10 and x to the power 12. At the same time, we don't need x to the power 12 from here. At the same time, anything more than x to the power 9, we don't need it from this. So, we are actually left with, we want to find out the coefficient of x to the power 9 in the expansion of, from the first polynomial, from the second polynomial, it's x to the power 6 plus x to the power 9. And from the third polynomial, we are getting 1 plus x square plus x cube, so on, till I will consider x to the power 9. That's it. Is it clear? So now, coefficient of x to the power 9. Now, if I multiply this with this, what we are going to have? 1 plus x squared plus x to the power 4 plus x to the power 6 plus x to the power 8. Now when x cube is multiplied, it's x cube, x to the power 5, x to the power 7, x to the power 9, bas, that's it. Then we will go for, when x to the power 6 is multiplied, we are going to have x to the power 6 plus x to the power 8, that's it. No more multiplication is needed for x to the power 6. And for x to the power 9, it's only x to the power 9, right? The other terms I have not written. You people can understand why it is so. Because this is exceeding x to the power 9. Now, this is in GP, so I can write this thing as 1 minus x to the power 10 divided by 1 minus x. So we need x to the power 9 in the expansion of 1 plus x square. X cube we are having only 1, okay. So 1 gone, x square gone, x cube gone. X to the power 4 we are having only one term. X to the power 5 we are not having, yeah, we are having. X to the power 5 only one term. X to the power 6 we are having two terms. X to the power 7 we are having one term. Two terms, so it will be 2. X to the power 8 we are having again two terms. And we are having x to the power 9 two terms, right? And this is 1 minus x to the power 10 into 1 minus x whole to the power minus 1. So from here we are only having 1. So we have to find out the coefficient of x to the power 9 from this expansion. Am I correct or not? 2x to the power 6, x to the power 7, 2x to the power 8, 2x to the power 9 into 1 minus x whole to the power minus 1. So what will be the coefficient of x to the power 9? When 1 is multiplied with x to the power 9 from this expansion gives us the coefficient 1. X squared, again we are getting the coefficient 1. For x cube 1, for x to the power 4 1, for x to the power 5 1, for x to the power 6 we are getting the coefficient as 2. For x to the power 7 we are getting the coefficient as 1. Again for x to the power 8 we are getting the coefficient 2. For x to the power 9 we are getting the coefficient 2. So total numbers we got is 1, 2, 3, 4, 5, 6 and 6, that's 12. And that's your answer. Is it clear? Is this problem clear to all of you? Have you understood this? See, in this kind of problems, when some scalar is multiplied with a variable, in that case, I cannot use the Bigger method because we don't know that method, right? So the best way to do, whenever you find that any scalar is multiplied with the the variables, we will always opt for multinomial theorem. Is it clear? Okay, let's take another problem. So this question, the question is find the number of positive integral solutions. Means here all your x, y, z are greater than or equals to 1. Positive integral solutions. For this inequation, we all know that for this inequation, I will introduce a dummy variable. Let us say the dummy variable be k, so that it becomes equals to 30. So your k is greater than or equals to 0. Am I correct? Because this inequation is less than equals to 30. It can be 30 or less than 30. Now when 3x plus y plus z gives us 30, then your k will take the value 0. And now if it takes the value 29, then k will take the value 1, and this thing goes on. Am I correct or not? Maximum what can happen? Your k can take the value 30. In that case, your 3x plus y plus z will all give us 0, right? Again, I'm telling you, somebody are thinking, sir, why you are saying that k will take the value 30? Because the minimum value that x, y, z can take is 1. So the minimum value of this expression is coming to 5. Then your k can take the value till 25. I agree with you. I absolutely agree with you. But as I told you, that don't consider that case here, because this will automatically be rejected when you will be finding out the coefficient of x to the power 30. That will automatically be rejected. So don't use your brain there. Okay, you consider the maximum value of k that it can take. Okay, and the minimum value of k that it can take. That's it. So we need to find out the coefficient of x to the power 30 in the expansion of x cube, x to the power 6, x to the power 9, and this thing goes on. Last term will be x to the power 30, right? For y, it will be x plus x square, x cube, this thing goes on till x to the power 30. For the third one again, the same thing. For z, we are going to have the same thing. So I'm putting a square over here. And for k, it will be 1 plus x square plus x to the power 30, the last term, right? So now let me just take out 3 from here, that is x cube. Let me take x outside, so x square will be out. So it is basically x to the power 5. So now we need to find out the coefficient of x to the power 25 in the expansion of 1 plus x cube plus x to the power 6 plus x to the power 27, right? And here it will be 1 plus x square plus x to the power 29 whole square, and this is basically 1 minus x to the power 31 divided by 1 minus x. Okay, GP series I have used. So I need to find out the coefficient of x to the power 25 in the expansion of this. So again, the first series is in GP, so I'm using the GP formula. The common ratio is x cube, and total number of terms are 10 divided by 1 minus x cube into, this is coming like, total number of terms are 30. So it will be 1 minus x to the power 30 divided by 1 minus x whole square. This is 1 minus x to the power 31 divided by 1 minus x. So we are actually having what? 1 minus x to the power 30 into 1 minus x cube. 1 minus x to the power 30 whole square, 1 minus x whole square. 1 minus x to the power 31 into 1 minus x to the power minus 1. Am I correct? So now I want to find out x to the power 25, so I don't need this one. X to the power 30 I don't need. So it's only 1. 1 minus x cubed to the power minus 1. Again, we don't need x to the power 30, so forget about it. Again, we are getting 1 from here. We are left with 1 minus x to the power minus 2. 31 I don't need. So again, 1 we are getting from here. And we are left with, just 1 second. This minus 2 will be outside. 1 minus x to the power minus 1, correct? So actually we are finding out x to the power 25 in the expansion of 1 minus x cubed to the power minus 1 into 1 minus x to the power minus 3. That's it. Okay? So now, we are actually having, for this expansion, we are actually having what? 1 plus x cubed plus x to the power 6 plus x to the power 9, x to the power 12, x to the power 15, x to the power 18, x to the power 21, x to the power 24. That's it. And this is 1 minus x to the power minus 3. Okay? I need x to the power 25. Now look at carefully. Here there is 1. When 1 is multiplied with the coefficient of x to the power 25 here, we are going to have the coefficient of x to the power 25. So here the difference is 2, right? 1 minus x whole to the power minus 3, the difference is 2. Okay, the difference is 2. So if I need x to the power 25, the coefficient will be 25. Here it will be 27. Plus, we are having x cubed. So I need x to the power 22 from here. That is C22. The difference is 2, so it will be 24 here. Now we are having x to the power 6, so I need x to the power 19 from here. So it will be 21. For x to the power 9, we want x to the power 16 from here. So x to the power 16, the coefficient will be 18, say 16. And for x to the power 12, we need x to the power 13 from here. So C13, 15 C13. For x to the power 15, I need x to the power 10. So C10, this will be 12. For x to the power 18, I need 7. From this expression, x to the power 7, so it will be C7, 9. For 21, I need 4. So this is 4, this is 6. And for x to the power 24, I need only x from here. So that will be 3C1. That's it. So if you add this, you are going to have our final answer. Let me just do it here. 27C25 is basically 27C2 plus 24C2, 21C2, 18C2, 15C2, 12C2, 9C2, 6C2 plus 3C1, that is 1. I'm sorry, 3. So we are actually having 27C2 is basically 27 into 26 divided by 2. That gives us 27 into 13. So it is 351. 24C2 means 24 into 23 divided by 2. That is 12 into 23, 276. 21C2 is basically 210. 18C2 is basically 18 into 17 divided by 2. That is 9 into 17. That gives us 153. 15C2 means 15 into 14 divided by 2. That is 15 into 7. That is 105. 12C2 is basically 12 into 11 divided by 2. That is 66. This is 36. This is 15. And this is 3. So now if we add, we are going to have 1215. Okay? And that's our answer. I hope this question is clear to all of you, right? Again, I'm telling you, I'm trying to illustrate all the possibilities that can happen. Okay? So now let's move for the next problem. Now in this question, they have said in how many ways we get a sum of at most 15. At most 15. Very important term. At most 15. By throwing 6 distinct dice. By throwing 6 distinct dice. So now, what are the outcomes on a dice? The outcomes are either 1, 2, 3, 4, 5 or 6. Let us say 6 dice are represented by x1, x2, x3, x4, x5. Let us say in this way, this xi actually represents number coming on the upper face of the dice. So what are xi? Xi is basically, what is I? I is from 1, 2, 3, 4, 5, 6. So all these x1, x2, x3, x4, x5 and x6, we are having 6 dice. So x1, x2, x3 till x6 are the numbers that are appearing on the upper face of the dice. Now, the question demands that if you add all those numbers which are appearing on the upper face of the dice, it will be always less than equals to 15. It will be always less than equals to 15. Is it clear? Where your all xi's are taking the values from 1 till 6. So in how many different ways this can happen? Again, it's a question of inequality. So what I will do here is I will simply introduce a dummy variable. Let us say the dummy variable be k, which gives us 15. It implies that your k is greater than or equals to 0. Is it clear? So now, what do you want to find out? You want to find out the total number of solution. Am I correct or not? So we have to actually find out the coefficient of x to the power 15 in the expansion of x plus x square plus x cube plus x to the power 4 plus x to the power 5 plus x to the power 6 whole 6. Have you understood this? Have you understood this? Because each dice can take the value from 1 to 6. So there are 6 such dice, so that is why I have raised its power to 6. Now for k, it will start from 0. So x to the power 0, x to the power 1, x square, and this thing goes on. Let us say the maximum value it can take x to the power 15. Again, I'm telling you, don't worry about the limit of k. You simply take that k is will go till 15. Because whatever unnecessary elements are there, it will automatically get, it will get rejected. So, if I take x common from this, actually x to the power 6 will come out. That is, we need to find out the coefficient of x to the power 9 in the expansion of 1 plus x square, x to the power 5 whole 6. And this is 1 plus x square till x to the power 15. So this can be written as what? We want to find out the coefficient of x to the power 9. This is in GP. So let me just apply the GP formula. Whole to the power 6 into 1 minus x to the power 16 divided by 1 minus x. So that gives us what? 1 minus x to the power 6 whole 6 into 1 minus x to the power 16 into 1 minus x whole to the power minus 7, right? So now, if I open this one, the first one, it will be 1 minus 6c1 x to the power 6, and I will expand no more, because after this you are going to have the exponent of x will exceed x to the power 9. So I don't need it. So now we are left with here 1 minus x to the power 16. I don't need x to the power 16, so reject it. We are left with 1 minus x whole to the power minus 7. So here we are having 1 minus 6x to the power 6 into 1 minus x whole to the power minus 7. And from here we have to find out the coefficient of x to the power 9. So here there is 1. Here it is 1. So I need x to the power 9 from this expansion. So it will be, again, let me just tell you again. Here the gap will be 6, right? the gap will be 6 everywhere. The gap is 6. So in this case, I need x to the power 9. So in this case, it will be, the coefficient will be 9. The gap is 6. So it will be 15C9 minus 6 times. X to the power 6 is here. So I need x's cube from this expansion. And the x's cube the coefficient of x's cube will be C3 9 because the gap is 6. That is why. So that will be my final answer. So 15C9 gives us 15 into 14 into 13. Achha, let me just do one thing. 15C9 is same as your 15C6 minus 6 into 9C3. So 15C6 will give us 15, 14, 13, 12, 11, 10 divided by 6 into 5 into 4 into 3 into 2 into 1 minus 6 times 9 into 8 into 7 divided by 3 into 2 into 1. So from the first one we are getting, the first one is given 5005 minus 504. So we are actually having the answer as 4501, and that's your answer. Is this conception clear to all? Have you understood this? You see, I have already introduced the inequation in the problem, right? So number of solutions, when inequation is also there, we can solve it. Okay, now let us take another problem based on this. Now this question is simply the conjugate of the sum that we have done right now. The question states, in how many ways we get a sum greater than 15 by throwing 6 distinct dice. In this case, what we got? In how many ways we get a sum of at most 15. Now, when you throw 6 dice, think about it. There are 2 possibilities. Whatever numbers are coming on the upper face of the dice, if you add, it will be either 15 or it will be less than equals to 15 or it will be more than 15. When you are throwing 6 dice, is there any other possibilities? Tell me. When you are throwing the dice, the sum will be either less than equals to 15 or it will be greater than 15. That's it. Now, less than equals to 15, just now we have solved and we got the answer as 4501. This is what? The total number of the sums that we are getting are less than or equals to 15. Now, in this case, we want that your sum should be greater than 15. So what I will try to do is, I will find out the total number of ways. Total number of ways. So whenever you are throwing 6 dice, you are getting some numbers on the upper face. So if you add those numbers, you are going to get a sum. Either this sum will be less than equals to 15 or it is more than 15. Now if we throw 6 dice, we are definitely getting 6 numbers. So now when you are throwing 6 dice, I want to find out what are the total possibilities of getting numbers on the upper face. When you throw the first dice, there are 6 ways. 6 ways of getting numbers. Similarly for the second, third, fourth, fifth and sixth. So total numbers that we are getting, so that if we add, we are either getting the sum less than equals to 15 or greater than 15 is 6 to the power 6. And that gives us 46656. This is the total number of ways of getting numbers on the upper face. Now we already got that the sum which are less than or equals to 15 and the total number of ways are 4501. Now if we subtract this result from this one, we are going to get a result which clearly indicates that the sum that we got on the upper faces of the 6 dice will be greater than 15. And in this case, the answer will be 42155. That's it. And that's your answer. Is it clear to all? Absolutely. Okay. Let me take another problem. The question is, find the number of positive integral solutions for x, y, z such that x into y into z is 24. Now, it is a problem with a different flavor. In this question, you have to find out all the positive integral solutions of x, y, z. That is, all your x, y, z are greater than or equals to 1. Now, you have to find out the positive integral solutions for this such that your x into y into z gives us 24. Now, this sum is a little bit different. Why? Because so far multinomial theorem, whatever we have applied, there we had plus sign in between, right? While solving these equations. But in this case, product is there. So now you have to, handle the sum intelligently. How to do that? Please check it. See, if we factorize this 24, we are actually getting 8 into 3, that is 2 cube into 3. Right? Now, your x can be, the factor x can be, let us say 2 to the power alpha 1 into 3 to the power beta 1. Okay? For y, it will be 2 to the power alpha 2 into 3 to the power beta 2. And for z, it is 2 to the power alpha 3 into 3 to the power beta 3. What does this signify? It signifies that your x, y, z, they will be either a multiple of 2 or it will be a multiple of 3. Okay? It cannot be a multiple of 5 because 5 is not present in its prime factorization. So either you will get 2 or you will get 3. Now, what are the possibilities of getting 2? Either you will have no 2, that is your alpha I can be equals to 0. Your alpha I can be 1, can be 2, can be 3 also. And your beta I can be no 3, that is beta I can be 0, or maximum it can take the value 1 because the power is 1. You cannot get other 3 out of it, isn't it so? We are only having 3 2s and 1 3. So other than that, you cannot go. So now, look at carefully. When we multiply this, x into y into z, we are actually having 2 to the power alpha 1 plus alpha 2 plus alpha 3 and 3 to the power beta 1 plus beta 2 plus beta 3. Is it clear? So now, one thing. Somebody can ask me, sir, they have written positive integral solution, then why you are taking alpha I as 0? See, the answer is very simple. Positive integral solutions means it is greater than or equals to 1. Now, if alpha I becomes, any of the alpha becomes 0, so it means what? It will become 2 to the power 0. What do you mean by that? It's basically 1. So 1 can be affected. There is no problem because this is an positive integral value. So I can take that value, right? So now, in this case, your alpha 1 plus alpha 2 plus alpha 3, this can be equals to 3 because there are only 3 2s available. So you have to distribute these 3 2s among these x1, x2 and x3. In how many different ways we can do? Now, remember this. Here, alpha 1, alpha 2, alpha 3, they are all greater than or equals to 0. So you are finding out non-negative integral solution for alpha 1, alpha 2 and alpha 3. So from the Vegas method we can say the total number of ways will be 3 plus 3 minus 1 C3 minus 1. That is 5 C2 ways of distributing these 3 2s among alpha 1, alpha 2 and alpha 3. Similarly, for beta 1 plus beta 2 plus beta 3, you are having 1. Again, in this case also, your beta 1, beta 2 and beta 3 all are greater than or equals to 0. Therefore, the total number of non-negative integral solutions will be 1 plus 3 minus 1 C3 minus 1. So that gives us 3C2 ways, right? Therefore, the total number of positive integral solution will be what? 5C2 into 3C2. So, because this and this now, you have to consider 2 and 3, not or 3, and 3. So that is why I have multiplied 5C2 with 3C2. So 5C2 gives us 10, 3C2 gives us 3. So answer is 30 ways. Is this clear? Is this problem clear to all? This is a different type of problem. Here your product thing is given. That is why I told you I have covered almost all types that can come in the examination. Okay? Now, let us use this multinomial theorem in some other problem, which is your grid problem. Though we have already done grid problem before in my previous classes, but here we will try to solve grid problems by using multinomial theorem. Okay? Now let us say there are n rows in a grid in which the first row has a squares, second row has b squares, third row has c squares, and so on. Nth row has n squares. Let me take the diagram like this. This is the first row of the grid which is having your a squares. This is our second row which is having b squares, and so on. This is the nth row which is having n squares. Now the question is, if we have to fill up those squares with alpha x, means we are having alpha number of x, and which has to be filled in these squares in such a way that at least one x is there in every row. In how many different ways we can do that? Is this question clear? We have been given a grid in which we are having some rows, and we are been given alpha x. X is it's an object, identical object. Alpha identical x has been given to us. The question is, you have to put those x in the squares in this grid in such a way that at least one x is there in each row. That's the question. Now, how we will do this? See the screen. In the first row, let me consider the first row only. In the first row, how many number of squares are there? A squares. Now, for the first row, we can either choose one square, or we can choose two squares, or we can choose three squares, or we can choose a squares. Similarly, for the second row, we are having b squares. So to place the x, we can choose one square, or two squares, or three squares, and so on. And the final, we can choose b squares altogether. Similarly for the third row, similarly for the nth row. So, is it not the same as finding out what is the coefficient of x to the power alpha? Why we are talking about x to the power alpha? Because ultimately whatever x you are putting, or whatever squares you are choosing from the grid, if you add those squares, what you are going to have? You are going to have the total number of x available to us. That is why it is same as finding out the coefficient of x to the power alpha. In the expansion, if we consider only the first row, as I told you right now, out of these a squares, I am choosing one square. So that can be done in AC1 different ways into x, because I am writing this thing in terms of polynomial. Why I have started with x? Because at least one x has to be there in each row. That is why I have to choose at least one squares from each row. So for the first row, it is AC1, that is I am choosing only one square. That can be done in AC1 different ways, into x plus means or. We can choose two squares. So that can be done in AC2 different ways, into x square. And this thing goes on. Maximum we can choose a squares because a squares are available in the first row. So it will be ACA x to the power a. Same thing with the second one. We are having b squares. So we can choose either one square or two squares or three squares. Maximum we can choose b squares. So that's exactly the polynomial I have written over here. I think it is clear to you. Now, for the third one, for the third row, we are having this same thing, and this thing goes on till our nth row, in which we will do the same thing. Either I can choose one square or I can choose two squares or we can choose n squares because there are n squares available. And the total number of ways in which this alpha x can be placed in this grid in each row such that no row remains empty. That is, at least one x should be there in each row. So this will be the total number of ways. Simply finding out the coefficient of x to the power alpha in this expansion. I hope it is clear to all of you, right? Let me take an example. See this question. There are 6x and that has to be placed in this grid in such a way that each row contains at least 1x. In how many different ways this can be done? You see, you can do this problem without using multinomial conception. You will simply say that there are 1, 2, 3, 4, 5, 6, 7, 8 squares are available. Now, out of these 8 squares, if I choose 6 squares, so that can be done in 8C6 different ways. It means what? You have chosen 6 squares. And in these 6 squares, you are putting the 6x which are available to us. Since 6x are identical, so there is no need to arrange among themselves because that can be arranged in only one way. So total number of ways of putting the 6x in this 8 squares is 8C6. Okay? Now you see, there are two ways where your 6 squares can be chosen in this way. In that case, this row remains empty. So that has to be subtracted because that is not our condition. Our condition is all the rows will have at least 1x. So I have subtracted that option. The option can be like this also. We have chosen, let us say, this 6 squares. In that case, this row will remain empty. Again, this is also not our case. It is not fulfilling our condition. So that also has to be subtracted from the total number of ways. Therefore, the total ways will be 8C2 minus 2. That gives us 8 into 7 divided by 2 minus 2. 28 minus 2. That gives us 20. So 26 will be the actual answer. This is when we are not using the conception of multinomial theorem. Straight away we have done this, right? Now let us try to use the multinomial theorem. Here, the total number of ways will be the coefficient of x to the power 6 in the expansion of, let me consider the first, let me erase this first. Let us first consider the first row. So from here, either you can choose one square or you can choose two squares. The same thing with the third row. So it's whole square. And for the second row, the total number of ways of choosing the squares will be 4c1x, 4c2x square, or 4c3x cube, or 4c4x to the power 4. Am I correct? That is we have to find out the coefficient of x to the power 6 in the expansion of, let me take a x common from here and a x common from here. So from here it will come x square outside. We are left with 2c1, that is 2c2, that is 1. So it is x whole square, and x is coming outside from here. So we are having 4c1, that is 4, plus 4c2 x I have already taken common. So it will be 4c2. So it is basically 6x plus 4c3 is same as 4, x square, 4c4 is 1. So it is x cube, right? So outside we are having x cube. So actually we need the coefficient of x cube in this expansion. Tell me yes or no. Okay. So now our task is to find out the coefficient of x cube in this expansion. So if I just open this, we are having four x squared plus x cube. We need the coefficient of x cube. So when this 4 is multiplied with x cube, we are getting the coefficient of x cube as 4. When this 4x is multiplied with this, that is 16, we are getting the coefficient of x cube. At the same time, when this is multiplied with this, we are getting the coefficient as 6, right? So the coefficient of x cube will be 26, and that's your answer. Is it clear? So we have done this problem without using multinomial theorem as well as using multinomial theorem. Why I've shown you multinomial? You can say, sir, multinomial theorem, here we are going for more calculation. No. Since this grid is small, it's easy for us to calculate it. But if the grids are more, then it will be little difficult for solving this problem by analytical method. In that case, your multinomial theorem will act as a blessing. Is it clear to all? Let me take another example. See this question. In how many ways the letters of the word person can be placed in the square so that no rows remain empty? Now the question is here, person, P-E-R-S-O-N. Here they are not identical, right? So they are distinct. So they can arrange in every arrangement, these 6 alphabets can arrange among themselves. Be very careful. In the previous examples, there was 6x which were identical. So I have not arranged between them. But in this case, for every arrangement, P-E-R-S-O-N, these alphabets can arrange among themselves also. So that has to be taken into consideration. Is it clear? Okay. So let me use multinomial theorem. For the first row, what we will say? How many number of alphabets are there? 6. So we need to find out the coefficient of x to the power 6 in the expansion of, let me consider the first row. It will be 3c1x, 3c2x squared, 3c3x cube. Okay. The same thing for this row and for this row. So it will be whole cube. For this row and for this row, it will be 1c1x only, because there is only one square for the second row. But this is the second row as well as for the fourth row. So it will be whole square. Is it clear? So now let me take x common from here, x outside here. So actually here we are getting x cube outside. 3c1 is 3, 3c2 is again 3x, and this is x square whole cube. And from here it is nothing because x square will come out. 1c1 is 1. So it is only x square. So we have to find out the coefficient of x to the power 6 in this expansion, right? Now already you have x to the power 5. So basically I need the coefficient of x in the expansion of 3 plus 3x plus x square whole cube. Is it clear? Now since x square is there, but I need only the coefficient of x, so this I don't need. So we are only finding out the coefficient of x in the expansion of 3 plus 3x whole cube. Okay. So now if we expand this, what we are going to have? 3 cube. Let me do one thing. Let me just first take 3 common. So it is basically your 3 cube into 1 plus x whole cube. I need the coefficient of x, so it will be 1 plus 3c1x. That's it. I will not go further. So it will be 3 cube into 3, right? So total will be 81. Am I correct? 81 number of ways are there in which the alphabets, of all the alphabets P, E, R, S, O, N, can be placed in this grid such that no grid remains empty. But in every case, as I told you in the beginning of the sum, that for every such arrangement, P, E, R, S, O, N, the 6 alphabets, they can arrange among themselves in factorial 6 different ways. Therefore, the total number of ways will be 81 into factorial 6. That will be your answer. Is it clear to all? So, in the previous sum, we are using multinomial theorem, but in the previous sum, all the alphabets were identical. That is why I have not arranged. But in this question, since the alphabets are, distinct, so I have to arrange those alphabets in every arrangement. That's exactly what I have done. Is it clear? Let me take another example. In this question, you have to place the letters of the word friend. F-R-I-E-N-D. Friend. In the squares of this figure so that no rows remain empty. Now again, the same thing as your previous sum. Here all the alphabets of the word friends, they are different. So in every arrangement, these 6 alphabets can arrange among themselves, right? So let me just use multinomial theorem. It is x to the power 6. We have to find out the coefficient of x to the power 6. If we consider the first row, what will happen? It will be 2c1x, 2c2x square. Same for the second row, so whole square. And for the third row, it will be 4c1x, 4c2x square, 4c3x cube, and 4c4x to the power 4, right? So let me just take out x from here and x from here. So outside there will be x square. This is 2c1 is 2 plus x whole square, and x is coming out. It's 4 plus 6x plus 4x square plus x cube. So we need to find out the coefficient of x to the power 6 here. Now since we are having x square and x, that is x cube we have already got. So I need to find out the coefficient of x cube in this expansion. Am I correct or not? I need to find out x cube in this expansion. Okay, so let me multiply this. 4x plus x square. I need to find out x cube. So when this x cube is multiplied with this 4, we are getting the coefficient of x cube as 4. When this one is multiplied with this, we are getting 16. When this one is multiplied with this, we are getting 6. That's it. So we are actually having 10 plus 16, that is 26. Okay. So there are 26 such ways in which these 6 alphabets of the word friend can be placed in this grid in such a way that no row remains empty. Now that's not your answer, because as I told you, all the alphabets of the word friend, they can arrange among themselves in every arrangement. So they can arrange among themselves in factorial 6 different ways. Therefore, the total number of ways will be 26 into factorial 6. Am I correct or not? You can do the same sum again without taking help of multinomial theorem. How? You will simply see that there are 8 squares. So in friend we are having 6 alphabets, so I need 6 squares at a time. So that can be done in 8C 6 different ways. So now you have chosen 8C 6 different ways, means you have chosen 6 squares out of 8 squares, right? Now in which, look it carefully, in which there are 2 ways when this 6 squares will be chosen, and in that case this row will remain empty, which I don't want. Similarly, if this 6 rows, these 6 squares are chosen, then we will be left with this row. Again, that also I don't want. So that has to be subtracted. So this will be the total number of ways. And in every case, the 6 alphabets, they will arrange among themselves in factorial 6 different ways. So the total number of ways will be 8C6 is same as 8C2 minus 2 into factorial 6. 8C2 is basically 8 into 7 divided by 2 minus 2. So this is 28 minus 2 into factorial 6. That gives us 26 into factorial 6. The same thing. Is it clear to all? I hope now this kind of problems, if it comes, you can handle it. If the number of squares in the grid are small, even if you don't use multinomial theorem, you can do it. But I will always suggest you, please try to apply multinomial theorem, because this will not only solve for those grids which are having small number of squares, but also for the grid which are having more squares. So it is better to remember multinomial theorem every time. It is my opinion. But if there are small squares, to do it quickly, you can use without using multinomial theorem, right? Okay, so now let's move for another conception, which is our derangement problem. Now, how does derangement problem is defined? It states that this is, again I'm telling you, this is a very, very important part. Very important part. So you people have to understand it very carefully. When n things are placed at n specific places, there are n things, and that n things are to be placed in n specific places, but none of them is placed on a specified position. Then we say that n things are deranged. What is the definition? Suppose we are having, let us say, there are 5 balls numbered 1, 2, 3, 4 and 5. And there are 5 boxes. Let us say we have numbered the boxes like 1, 2, 3, 4 and 5. Now you have to place one ball in one box. Only one ball can go in one box. In how many different ways you can place those 5 balls in the 5 boxes such that no balls should be in its right box? That is, ball number 1 should not be in box 1. Ball number 2 should not be in box 2. And this thing goes on. That is, no balls are placed in its respective box. In how many different ways you can do that? This is a problem for derangement. Is it clear to all of you? Absolutely. Now let us see how to solve this derangement problem. Let us consider that there are n letters. And let me denote it by L1, L2, L3 and so on, Ln. Okay, there are n letters and there are n self-addressed envelope. There are E1, E2, E3 and so on. Is it clear? And at the same time, let me denote AI. AI is what? AI represents that the ith letter will be in the EI envelope. Is it clear? So what do you mean by AI? AI is the ith letter will be in its right envelope, which is EI. That is, the first letter will be in the right envelope. If I say A1, what do you mean by that? That is, the first letter will be in the envelope E1. If I say A5, what do you mean by that? The fifth letter will be in its right envelope E5. Is it clear? Now, what do you want? I want that the first letter should not be in its right envelope. That is A1 bar. And the second letter is also not in its right envelope. That is A2 bar. Similarly, the third letter and so on till the nth letter. They are not in their right envelope. Now, from the De Morgan's law, we can write this thing as A1 union A2 union A3 union AN whole complement. This is again from the De Morgan's law. This you people have all covered in set theory. So this can be written as total minus n of A1 union A2 union A3 union AN. Okay. Now, from the principle of inclusion and exclusion, we can write this thing as total minus sigma n A1 minus sigma n A1 intersection A2 sigma n A1 intersection A2 intersection A3, and this thing goes on. The last one will be minus 1 to the power n minus 1. N of, n means the cardinal number of that set. So A1 and A2 and A3, and this thing goes on till AN. Okay? So this is the total number of ways in which all the letters are placed in wrong envelope, which is your A1 bar and A2 bar and A3 bar, so on, AN bar. Is it clear? Now, what do you mean by sigma A1? What do you mean by sigma NA1? It means actually NA1, NA2, NA3, NAN. Actually, what do you mean by that? It means when the first letter is in its right envelope, in how many different ways you can arrange all those letters. NA2 means what? The second letter is in its right envelope, that is E2. In how many different ways you can arrange that? Okay? N3 means the third letter is in its right envelope. In how many different ways you can arrange all those letters when the third letter is in the right envelope. I don't care about the other letters. The other letters can go to its self-addressed envelope or it may not go to its self-addressed envelope. That is not my concern when we are considering NA3. NA3 means we are only concerned about that your A3, that is the third letter, is placed in its right envelope, E3. That's it. So for each one of this, if we consider that A1 is in its right envelope, will be same as when we are considering that A2 will be in the right envelope and so on. So out of these n letters, in how many different ways you are choosing one letter, only one letter you are choosing, which you are placing in its right envelope. Out of these n letters, one letter can be chosen in NC1 different ways, Okay. So let us consider that A1 came. Now we have placed this A1 in its right envelope, and which can be done only in one way. And we are left with n minus 1 letters and n minus 1 self-addressed envelope. In how many different ways these n minus 1 letters can go in this n minus 1 self-addressed envelopes? It can go in n minus 1 factorial different ways. Again, I am mentioning when we are considering A1, that is A1, the first letter is in its right envelope, that is in E1. I am less bothered about the other letters, where it is going, whether it is going to the self-addressed envelope or not, that I don't know, and I am less bothered about that. I am only concerned about that my A1 letter should go in its right envelope. That's it. So in this way, your A2, A3, A4, AN, this can be all done in NC1 different ways, because you are choosing one letter at a time. Okay. Now, for the second one, what is A1 intersection A2? What is sigma A1 intersection A2? Look at carefully. We are actually taking two letters out of these n letters. The all possible combinations of choosing two letters from this n letter is nothing but NC2. This is the way, the total number of ways in which two letters are chosen from the n letters, and now they are placed in the right envelope. That can be done in one way. And now we are left with n minus 2 numbers of letters and n minus 2 numbers of self-addressed envelope. So n minus 2 letters can be placed in n minus 2 envelopes in NC2 different ways. N minus 2, not NC2, I'm sorry, n minus 2 factorial different ways. Yes or no? There are suppose you have chosen two letters. Let us say A1 and A2. A1, A2 means what? You have chosen two letters 1 and 2, and they are placed in their right envelope E1 and E2. Now we are left with n minus 2 letters and n minus 2 envelopes. So this n minus 2 letters can be placed in this n minus 2 envelopes in n minus 2 different ways, n minus 2 factorial different ways. That's exactly what I have written in case of n A1 intersection A2. So this one will be NC2, two letters placed in the right envelope in one way, and the other n minus 2 letters are placed in n minus 2 envelopes in n minus 2 factorial different ways. Similarly, for the third one, it will be NC3, 3 letters are chosen, placed in the right envelope in one way, and the other left n minus 3 letters are placed in n minus 3 envelopes in n minus 3 factorial different ways. And this thing goes on, right? So in the last one, what will happen? There are n letters you have already chosen. So that can be chosen in NC1 or one different way. It's all same because I want to make a formula. That is why I'm writing it as NCN. Now all are placed in their right envelopes in only one way. That's it. No other letters are left. Okay. So it will be total minus. Let me just open this. NC1 means factorial n divided by factorial 1 into n minus 1 factorial into n minus 1 factorial minus NC2 is factorial n divided by factorial 2 into n minus 2 factorial into n minus 2 factorial plus NC3 means factorial n divided by factorial 3 into n minus 3 factorial into n minus 3 factorial. Simply I am using the formula, nothing else. Minus 1 to the power n minus 1. NCN is factorial n divided by factorial n into factorial 0. That's it. Okay. Now you observe one thing. This thing goes off. This thing goes off. This thing goes off. Right? So we are left with total minus n by factorial 1. Factorial n by factorial 1 minus factorial n by factorial 2. Factorial n by factorial 3, and this thing goes on. Minus 1 to the power n minus 1 into factorial n by factorial n. Okay. Now, what do you mean by total? Total means when there is no restriction. We are having n letters and we are having n envelopes. This n letters can be placed in this n envelope where there is no restriction is nothing but factorial n. So total is basically factorial n. Now let me open the brackets. Is it clear to all? Okay, so I can do one thing here. I can take factorial n common. So we are left with 1 minus 1 by factorial 1, 1 by factorial 2, 1 by factorial 3. This thing goes on. Plus, you can do one thing. You can take this minus 1. Actually, we are having minus this thing, right? So we can write this thing in this way also. Minus 1 to the power minus 1 will give us minus 1 whole to the power n. So this I can write it as minus 1 whole to the power n into 1 by factorial n. That's it. Okay. And this is the total number of ways of derangement of this n letters. And it is denoted by dn. So what is dn? dn is factorial n. 1 minus 1 by factorial 1, 1 by factorial 2, this thing goes on, minus 1 to the power factorial n into 1 by factorial n. That's it. Is it clear to all? Is this clear to all? We have to remember this formula. This is as a formula we have to remember that the derangement of n objects is dn. We represent this thing as dn, which is equals to factorial n into the whole thing which is given to you. 1 minus 1 by factorial 1 plus 1 by factorial 2 minus 1 by factorial 3, and this thing goes on. So we have to remember this way, right? Now let us just consider some initial problem. That is, what is my D1? What is D1? What do you mean by D1? That is, there are only one letter and one self-addressed envelope. In how many different ways you can derange this? 0. One letter and one envelope. Can you derange it? Can you put that one letter in an envelope which is not its right envelope? You cannot do that. So your D1 is 0. What about D2? What is D2? D2 is basically there are two letters and two self-addressed envelopes. In how many different ways you can derange them? See this one? Suppose this is my two letters, letter 1 and letter 2, and these are say two envelopes. Let us say E1 and E2. Now in how many different ways you can derange these two letters? There is only one way. The way is your L1 is placed to E2 and E1 is placed to L2. That's it. So D2 will be nothing but 1 because there is only one way of deranging these two letters. Okay, let us consider what is D3. D3 means there are three letters now. Let me just erase this. Now we are having three letters, L3, and we are having three envelopes, E1, E2 and E3. Now let us place letter L1 in E2. If letter L1 is placed in E2, then your L2 can go in L3 and L3 can come in L1. This is one way. Yes or no? When L1 is placed in E2, now let us consider that your L1 is placed in E3. That is, your letter 1 is placed in envelope 3. Then your L2 will come in E1 and L3 will come in E2. That is another way. Yes or no? So these are the only two ways when three letters and three envelopes are given to us and we have been said to find the number of ways to derange them. So there are three ways. Yes, I'm sorry, two ways. Am I correct? So these are the initial values which we may remember. It will be helpful for us in the coming days. D1 is 0, D2 is 1 and D3 is 2. You can verify, you can cross check it with your formula also. What is D3? Your D3 is, we got it as 2. Let me check it from the formula. D3 will be factorial 3 into 1 minus 1 by factorial 1 plus 1 by factorial 2 minus 1 by factorial 3. This goes off. So factorial 3 into 1 by 2 minus 1 by 6. So that gives us 6 into 2. So 6 and factorial 3 goes off. So we are having 2 waves. Exactly the same answer that we got here. Is it clear to everyone? Is this clear to everyone? Have you understood? So this is as a formula we have to remember for derangement. Okay, because derangement problem is widely used everywhere, I'm telling you. Particularly in functions, when we will do functions, we will see that this derangement problem will come there. Okay, so have you understood this? Let me take an example for this. Say this question. A person writes letters to 6 friends and addresses the corresponding envelopes. In how many ways can the letters be placed in the envelope so that all the letters are in wrong envelopes? That is, there are 6 letters and 6 self-addressed envelopes. We have to find out that all the letters should be in the wrong envelopes. Means we are actually talking about what is our D6. What is our D6? That is, 6 letters are deranged. Okay, that is, they are not in their right envelopes. So what will be D6? It will be factorial 6 into 1 minus 1 by factorial 1. I'm directly applying the formula. Okay. So this is factorial 6 into 1 over 2 minus 1 over 6 plus 1 over 24 minus 1 over 120 plus 1 over 720. So we are actually having factorial 6 into, let me take the LCM, which is coming to 720. And this will be 360 minus 120 plus 30 minus 6 plus 1. So actually we are getting factorial 6 into 720 means factorial 6. And in the numerator we are getting, it is coming to 265. So factorial 6 goes off. So it is 265. That is, your 6 letters are deranged in 265 different ways. So the first answer will be 265. I hope it is clear to all. Now the second question is more interesting. It states that at least 2 of them are in wrong envelopes. That is, in this case, I don't want that all the 6 letters should be in the wrong envelopes. No, I don't want that. What I want, that at least two of them will be in their wrong envelopes. That is actually what you are saying. At least 2 means what? At least 2 letters will be in wrong envelopes. What do you mean by that? That is, 2 letters are in wrong envelope and the rest 4 letters are in the right envelope. Or 3 letters are in the wrong envelope and 3 letters are in the right envelope. Or 4 letters are in the wrong envelope and 2 letters are in their right envelope. Or 5 letters are in the wrong envelope. Just 1 second, this will be wrong, right? This will be in the wrong envelope. So 5 in the wrong envelope, 1 in the right envelope, or 6 are in wrong envelopes. Am I correct? Now, think about it. 2 letters will be in their wrong envelope and 4 letters will be in their right envelope. My first question is, which 4 letter we are talking about? So it will be 6C4. These 4 letters are in their right envelope, which can be done in only one way. And 2 letters will be in the wrong envelope, which is actually talking about D2. Plus 3 letters will be in their right envelope. So that can be done in 6C3. Which 3 letters? 6C3 number of ways are there of choosing 3 right letters, which are in their right envelope, which can go in only one way, in their right envelopes. And 3 will be in the wrong envelope, means we are finding out D3. Again, 2 letters will be in the right envelope. So which 2 letters? 6C2. They are in the right envelope. And the 4 letters are in the wrong envelope. So into D4. Plus 1 letter is in the right envelope. Which letter? 6C1. Right envelope. It will go in only one way. And the other 5 letters will be deranged. And here all the 6 letters are deranged. So if you calculate this, you are going to get your answer. Okay? Let me just do it. 6C4 is same as 6C2, which gives us 15, D2. 6C3 is same as 20, D3. 6C2, again, it is same as 15, D4. 6C1 is basically 6, D5 and D6. So what will be the answer? We have already said that your D2 is basically 1. So this is 15 plus D3, as I told you, it is 2. We have already said that D1 was, the initial problem, right? D2 is your 1 and D3 is 2. So it will be 20 into 2 plus 15 into D4. What is D4? Factorial 4, 1 by factorial 2. I am writing it from 1 by factorial 2 because 1 minus 1 by factorial 1, that gets cancelled. 1 by factorial 3, 1 by factorial 4. So that gives us factorial 4 into 1 by 6, 1 by 24. So factorial 4, 24 is here, 12. 24 plus 1. So it is basically 9. Am I correct? So 15 into 9 plus 6 into D5. What is D5? So we are having factorial 5. Factorial 5, 120 goes off, so it is coming like 44. So 6 into 44, and just now we have calculated D6 as 265. So our final answer will give us 15 plus 40 plus 135 plus 264 plus 265. That gives us 719, right? 719. So at least 2 letters will be in wrong envelopes. The total number of ways, 719. Have you understood this? Okay, we can do question number 2 in some other way also. Okay, let me just write the answer here so that we can match our answer. It is 719. And what is the answer? Let us check. Yes, it is 719. Okay. Now, the second problem can be solved in another way also. How it can be solved? At least 2 letters are deranged. It means what? The total number of ways of arranging the letters in the in the 6 envelopes, total number of ways, minus at most one letter is deranged. Okay? So what is the total number of ways of arranging 6 letters in 6 envelopes? That can be done in factorial 6 different ways. Minus at most one letter is deranged, means no letter is deranged or one letter is deranged. Now, no letter is deranged. No letter is deranged. That is, all the letters, all the 6 letters, they're in their right envelopes. So that can be done in one way. And what is your D1? D1 means one letter is deranged, while the other 5 letters are in their right envelopes. Now, when the 5 letters are in the right envelope, then we are left with one letter and one envelope, which is the self-addressed envelope. So, one letter cannot be deranged when 5 letters are in their right envelopes. Hence, D1 is 0. 0 ways. So, total number of ways where at least 2 letters are deranged is 720 minus 1, that is 719. In that way also you can do it. But have you understood this problem? Is it clear to you? In the particularly the second part is more interesting, where they have said that at least 2 letters should be in the wrong envelopes. That is, at least 2 letters should be deranged. It means what? That 2 letters are deranged, the rest 4 letters will be in their right position. Or 3 letters are deranged, the rest 3 letters will be in their right position. And so on till 6 letters. So I have solved it in 2 ways. Either you can do by this way, that which 3 letters are in the right position, choose that letters first, and then you derange the remaining letters. In that way also you can do. Or you can do by total minus at most one letter is deranged. And we all know that one letter, if I say only one letter is to be deranged, you cannot do it. You take any number of letters and any number of envelopes, and if I ask you, only one letter has to be deranged, it is not possible. Answer is 0. Is it clear? Is this derangement problem clear to all of you? Absolutely? Okay. So that's all for today's class. I hope you have enjoyed the topic I have discussed today. So see you very soon in my next video. Till then, stay tuned to us and don't forget to subscribe, like and share this video. Thank you so much. Take a very good care of yourself.